We start Physics 2 with thermodynamics, which in many ways is an application that just follows on from what we did in Physics 1, although it doesn't feel like that because now we're going to be talking about heat and temperature. So we're going to have a new fundamental unit, right? So we have temperature in our MKS system. We're going to stick with Kelvin, which I expect you know, or degrees Celsius. Now, if there are many instances where you can just use this, but if you're ever in doubt, go ahead and convert to Kelvin. But these are the units we'll need to be in. So anytime you're in Fahrenheit, go ahead and make the conversion. You know this from doing this in chemistry, for example. So temperature is at least operationally what we measure with a thermometer, right? But what it's really tied to is actually the kinetic energy of atoms. At least in an ideal gas situation, it's the kinetic energy of ideal gas particles as they're moving around. So this is a measure of thermal energy. And you may remember back in Physics 1, we talked about mechanical energy and then thermal energy associated with when we had friction. So of course, that's a way we can change the temperature. So temperature is a quantity that we associate with an object. We measure it with the thermometer, but it is a measure of the internal energy of the system. And so we're going to start by looking at sort of the properties of materials as we change temperatures, and we'll start with solids and then liquids, and then we'll go to gases, and we'll spend more time there because it's easier to make the connection between this and our ideas of work and energy when we start talking about a gas, particularly an idealized gas. But to start with the solid, one of the things that we know that happens when we change the temperature of a solid is we can have expansion. So thermal expansion. And most materials expand when they get heated up. Water is an odd example where, I know it's not a solid, but water is the odd case where it goes through sort of this dip. It expands above 4 Celsius and below. 4 is kind of a minimum there. So as it's going into its crystalline ice phase. Okay, so thermal expansion for most materials. Metals expand more than, metal conductors expand more than insulators in general. And we can often describe thermal expansion by saying, as we heat something up, as it expands, it can get longer, for example. And so this extra length right here, delta L, is related to how long the material is to start with. So how long it is, what the change in temperature is, and then alpha, which is just this coefficient of linear expansion. And in many instances, this is just a constant, and we look it up. It's not very big because things don't get really big as we change their temperature. Excuse me. But this is called the coefficient of linear expansion because it's for one dimension. So I mean, I made it like a ruler, but think of this as just expanding in one dimension, linear expansion. Now, it's worth doing because we do this a lot in physics just to check to see how things work out. If you want to look something like this up, you need to know something about the units. And so on this side, the change in length would be in meters. Meters are our length unit. So I've got then that the units of alpha, so I do units by putting a bracket around it just to remind myself I'm finding the units, need to be 1 over degrees Celsius, degrees centigrade, or 1 over Kelvin. And either works here because we're taking the difference in temperature. So this delta, if you remember from Physics 1, is about saying the change in temperature. So that's equal to temperature final minus temperature initial. And the difference in temperature in Kelvin and Celsius is exactly the same, right? 100-degree difference in Celsius is the same as a 100-degree difference in Kelvin. That's not the same for Fahrenheit because it's a different scale. So these are our units, because once we have that, that will cancel with the units here and we'll be left with meters. Okay, so that's really supposed to be one dimension. In 2 dimensions, so in 2 dimensions, if I have something more rectangular, then what happens is if one end is sort of, well, we'll just do the expansion all the way around like this, because that's typically how it happens. That's, again, an exaggerated view, but we can say that this change in area is approximately equal. I mean, these are all approximations because it's not linear over every possible temperature. This is not true in the middle of the sun, for example. We've got phase changes and things like that. But it works for a fairly good range of materials. Is 2 alpha times the original area times the change in temperature. And you won't be surprised to hear that the volume does the same thing. Okay? So you can have the same expression for volume. Sometimes the change in volume is written as 3 alpha V naught delta T, and sometimes this is written as a beta. So you'll see it both ways. Something to think about here is if we have a material like this that has a hole in the middle, and we think about it expanding, well, it's not too hard to say, okay, this part expands. But then we have to ask a question about whether we think the expansion is sort of expanding into the hole or out of the hole. And I hope you can see that the argument is, the idea of expansion is that you're separating from each other. Sort of a toy model of this is to think of the atoms increasing in energy, so they're kind of bumping around more. That's not really the picture, but that gives you some idea. They are moving more. And so they want to so they're spreading out, and coming into the center is not a spreading out, right? They're getting closer together there. So in fact, the expansion, the whole, even gets bigger as well. Okay, so you should convince yourself that's the case. And so what you can do is you can use this in situations where you've got 2 different materials and you want to get them apart from each other if one of them has a higher coefficient of expansion than another. A place where I often use this is when I have a jar of pasta sauce. The lid is usually, okay, I'll try to draw a jar here and we'll see how this goes. Okay, so there. So the lid is usually metal in the jars that I bought, and this is a glass jar. And so if I can't get this metal unscrewed from the glass, then what I will do is I will run this under hot water in the sink for just a little bit, which will make the metal expand more than the glass. Again, I need that ring to expand because metal has a higher, so this has a higher alpha than the glass does, and so it expands more, and so that makes it looser and easier for me to take it off. Now this is not going to work if I've got 2 materials of the same thing, if I have metal on another metal that's basically the same. But when I have 2 materials that are different, this is a nice way to do this. Another way this is used is this is a way to fit materials onto each other. So if you have, for example, a metal rod and you're wanting to fit a ring on it of some sort for a gear, or even just because you need a collar on it of some sort, then you can take this ring, right, and if you heat it up, slide it in place and then cool it down, it's not gonna, if you set these up right, if the tolerances are right, then it's actually not gonna come apart until you heat the whole thing up. But that's a way that is used to fit things together. So these have some applications, but this is just sort of a start at looking at one property associated with temperature changes.